I've said many times that Europa is one of the most exciting places to search for life in the solar system. We've got this vast liquid ocean underneath a thick, icy shell. There is probably volcanism that is injecting chemicals and rock into this ocean. And that is the kind of habitat that we see at the bottom of the oceans on Earth. And so if life seems to be at the oceans on Earth, could life be at the bottom of the oceans on Europa? Could we have the European space whales? My guest today is Dr. Paul Byrne. He's an associate professor at Washington University in St. Louis, and he recently published a devastating paper on the habitability of the subsurface oceans on Europa. So if you want to sort of hear why Europa might not be such an exciting place for life today, but why it might have been maybe more habitable in the past and might be again in the future, I think you'll really enjoy this conversation with Dr. Paul Byrne. Paul, I have credited you with single-handedly building my interest in Venus, and you have saved it from me pushing it into the sun, which I've mentioned.
I appreciate that. I appreciate that restraint you've had.
Yes. But now you've come to take something away from me, and that is my deep enthusiasm and the search for the European space whales.
Right.
So, you're a monster.
And I'm not even sorry. You know what?
Actually, oh my God.
So there's two parallel parts of this conversation, right? There's sort of the near term of what we're going to talk about in this study. And there's the larger topic of what humans want to find out there. And it really interests me, and it has for a long time. But yeah, I think the TLDR of this is that I think it's unlikely that there are European space whales, at least today.
Right. Okay, so the traditional idea here is that, we found life at hydrothermal vents on Earth.
Right.
It's completely cut off from the surface of the world. We know that there are tidal activity. There's probably a vast ocean underneath the ice on Europa. Therefore, ... there could be life under the water on Europa.
Right.
And I guess, what is the key to that there could be life on Europa? What's the expectation that the scientists have been having?
Right. So generally, when we think about life and environments on life, there's generally, although this is admittedly the minimum requirements, it's almost like an oversimplification, but we think there are at least three fundamental requirements that you have to satisfy for an environment to at least be deemed habitable, and we'll get to whether that means inhabited, but habitable. So the first one is liquid water. And that is because everywhere on Earth where we find water, no matter how much, tiny water vapor or water trickling on the ground or seas or oceans, we find life. So water seems to be an inherent requirement in an environment that has life in it, because of course we are the ugly bags of mostly water, right? To paraphrase a Star Trek episode. So water is inherent to the life, at least as we know it. And let me just back out for a second and say, this is for life as we know it.
Right. Yes. Obviously people are going to be like, why don't you guys look for life as you don't know it? And obviously,
like, how do you begin
to search for life as you don't know it?
Exactly.
Right. Exactly. As soon as you know it, then you search for it. So
start with something that we know, right? It doesn't mean that there aren't other forms.
Yes.
Okay. So liquid water. The second thing you have to have is organic chemistry, because the life as we know it requires these long chain hydrocarbon molecules. These organic carbon molecules that have carbon, hydrogen, oxygen, sulfur, nitrogen, phosphorus, these kind of foundational biomolecules that you have for life. And the thinking goes that if you have an environment in which you find organic chemistry, then you at least have the building blocks for what we would refer to as life as we know it. And what's been really, really interesting in the last 20 years in particular is that wherever we look in the solar system, we're finding more and more evidence of these organic compounds, not just the building blocks, the carbon, the hydrogen, oxygen, but even like longer chain molecules that we know ultimately can go in, esters and ethyl molecules. And what that suggests is at least the foundational stuff that goes into making life as we know it is widespread, from Mercury all the way to the outer solar system, to comets and asteroids. So that's encouraging, right? So at least the components are there. And the third thing you need is some kind of energy source to make all of this work. And what's particularly exciting about Europa is that we don't know 100%, but we know very strongly suspect that it has a subsurface liquid water ocean. That was something that was picked up by missions that we have sent past Europa in the past, and it is one of the purposes of the Europa Clipper mission, which NASA launched in late 24, to basically go and actually assess for sure, is there an ocean and what are its properties. So big body liquid water, check. We know on Europa there are organic compounds. We see evidence of this in the outer part of the shell. So if you've ever seen pictures of Europa, it's this kind of, pretty cue ball thing. It's got an icy exterior, but it's riven by these lines, which are kind of orangey. And these things look like they've got organic compounds in here that are potentially, some of this is sourced from Io, but some of this is potentially sourced from the ocean, and it gets up through the ice through mechanisms that we don't necessarily understand all that well, but we have strong reason to suspect there's organic chemistry there. And we know in another so-called ocean world, which is little diminutive Enceladus orbiting Saturn, this thing is actually the only world for which we definitively know there's a subsurface ocean there, because we can see pictures of it. We can see this stuff blasting out through fractures in the south pole of Enceladus. And when the Cassini mission flew through these plumes, it detected, in addition to water and ice particles, it detected lots of organic materials. So again, the thinking goes that there's probably almost certainly organic chemistry of some kind happening inside Europa. And then you have the energy question. Well, most of what we're familiar with life on Earth is photosynthetic. It directly or indirectly lives off the sun. But it was the discovery in the 1970s and 80s of these so-called hydrothermal systems deep underwater, the black smokers in particular and white smokers, that got a whole pile of people excited, because we discovered these huge chemosynthetic environments. As opposed to photosynthesis, these are using chemosynthesis. They're using chemicals in their environment to basically produce life and importantly, to sustain it. Right? It's not just that you have life there, but this life can live there for a while.
Right.
And so,
you look at Europa, it is right next door to Io, and Io is the most volcanically active place in the solar system. It's covered in volcanoes.
Right.
And you know that same process that is potentially creating a liquid ocean on Europa is that same sort of tidal effect that's happening. And so it feels like a really natural thing to go,
it feels like you're
right?
taking all three boxes. You have the liquid water ocean, you have the organic chemistry, and there's some kind of energy source that's coming potentially from these tidal interactions. You're dead right. And so if you look at Io, which is crazy, this thing, the current count, as I understand it, for a number of impact craters on Io is 1. Right? Like we're up to 1. It had been thought to be 0. Maybe it's 1. It's not definitively. Right?
And that's because of the volcanism. It's just resurfacing.
It's because this thing is undergoing volcanism the whole time. Every time we've ever set a spacecraft near Io, it has some or other volcanoes are erupting. So this thing is going crazy. And there's a really interesting story that just prior to the flyby of Voyager 1 in the 70s, a paper came out 3 weeks before, led by Stan Peel, in which they had predicted that they would find lots of volcanic activity because of the nature of these tidal interactions. And lo, 3 weeks later, they verified this. So we know that Io is crazy volcanic. And the reason it is because it is in a particular, we call it a Laplace resonance. But basically what that means is that it is in a particular situation where not only is it undergoing tidal effects the way Earth does because of the moon, but it's undergoing so much tidal effect because it's being squeezed between Jupiter and then Europa and Ganymede, which are farther out. And so it just so happens that there's a lot of this tidal energy producing an enormous amount of power for Io. So a natural question is, well, could this apply to Europa? And in fact, we know that Europa is subject to tidal stresses because there are cracks. I mentioned these cracks in the exterior icy shell, and there are cracks that have very particular kinds of shapes and patterns to them, which really are only explained by there being the effect of tidal stress. So for a long time, there has been, if not necessarily knowledge, a working assumption that we might find those 3 ingredients together deep inside on the seafloor of Europa that could potentially provide
and that's been reinforced with those observations from Enceladus, as you said, that it flew through the plumes at Enceladus. It found dissolved hydrogen gas. It found organic molecules, definitely water.
Yeah.
So you've got all of the fixins for this,
all of them,
chemical synthesis, and I mean, it's almost like we're willing into existence those plumes to exist on Europa, but they haven't been found yet.
And the whole story of plumes in Europa is an interesting one, right? A paper came out in 2014 using Hubble data, in which it was reported that there was evidence for what looked like some kind of plume on the surface. A lot of follow-up observations since then, including by that original discovery team, have not returned any more observations since then. Now, even Webb. Yeah. But at the same time, it's very difficult to know what to make of that first detection. One explanation is that it's a plume in the manner of Enceladus, where this is ocean material coming up through a fracture and somehow getting into space, and we're seeing essentially the spectral signature of this. an asteroid striking the ice might produce the same result. Or maybe they are plumes, but they only go every 100 years because of whatever conditions are required, and of course, every 100 years is extremely rapid geologically, but not if humans are waiting impatiently to see it. And so that's why Clipper, it's another thing that Clipper's going to do. It's going to search for plumes, but it's also going to be able to see whether there are places where we might reasonably expect to find evidence of there having been plumes, even if they're not there anymore. So it's another reason why this mission is so important. It's going to tell us an awful lot about the moon that we don't know right now. So this gets to the question of, to your point of willing into existence, are there the conditions within Europa that are ripe for life? Now, this is another point where we should take a moment and step back and say, we don't know how life gets going, right? We don't know that. We do know that it has to have happened at least once on this world. We use the term abiogenesis to describe the idea of life emerging from non-life. And like I said, the things that underpin life appear to be very common. And so certainly my own view is that I don't know if life is necessarily difficult to get going. What we did with this study was to try and answer the question from a tectonic perspective. So a lot of what I do is thinking about how rocks behave and deform under things like stress. And a lot of what I've done in my career has been the inner solar system. But what's worth reminding folks is that if we look at the outer solar system for things like Enceladus or Titan, Dione, Europa, Ganymede, these are predominantly rocky bodies, just like the inner solar system. They just happen to have a lot of water on top relative to, say, Earth. But if you look at the absolute diameter of Europa, only the upper few percent is ice and water. The rest of it is going to be presumably rock and probably metal, of the actual details that are not well understood. So you can think that in terms of by volume and by mass, Europa is principally a rocky body. And so this whole thing started years ago, well before the pandemic, where a friend and I were just chatting one night on WhatsApp. And the conversation got around to, what would the seafloor of Europa look like today? Like, forget the science. Just if I were to fly over it in a submarine or photograph it, what would it look like? Would it be replete with towering cliffs and mountains and valleys? Would it have chains of volcanoes? Or would it look like perhaps, the deep, deep abyssal plains of Earth's oceans where there's really not a lot happening? And so I assumed there would be a lot of stuff in the literature at that point talking about this environment. And I was surprised when I found that there wasn't. There hadn't been very much. There'd been some, but nothing compared to the amount of focus on the outer part of the body, which unsurprisingly, it's the bit we can see, right? And so the problem with trying to figure out what's going on with the ocean floors of these worlds is that we have virtually no direct evidence of anything. So we have to go and try and use, first principles, what do rocks do? And that's what we did.
Right. What do rocks do?
Yeah, pretty much. And so basically the idea here was to figure out, if you assume, we make some basic assumptions. We assume that it's rock that you get everywhere, right? And there's good reasons why these are all just assumptions. And this is all modeling. And we have spent years working and refining the model, but it's still just a model. Right?
But didn't Jupiter do you a favor by tearing off any water around Io to sort of show you what it is probably made of?
So arguably it did. And we also have a favor of the fact that everywhere we've sent spacecraft to these objects that are big enough to pull themselves into a round ball, that are under this hydrostatic equilibrium, any of these worlds has shown evidence for volcanic material. And this volcanic material, okay, this is the caveat for geochemists who are listening to this. This is the bit where you want to turn the volume down. It's going to upset you. As far as I'm concerned, all basalt.
We'll put a spoiler alert here when you can return.
It's all basalt. It's all the same. Now, geochemists are like, they're all different. Okay, I understand that. Yeah. But in the grossest scale, basalt, or to Americans, basalt, but it's basalt, is the same stuff everywhere. And you see it. It covers most of Mercury. It covers most of Venus. It covers the ocean floors of Earth. It covers a good chunk of the moon and the Maria. It covers much of Mars. We see it covering almost all of Io. We even see bits of basalt on Vesta, which isn't big enough to have pulled itself into a ball. But
so it just have volcanic eruption stuff.
It's the sort of default. If you don't change any of the parameters and you get stuff melting in the inside and coming on the outside in a rock, you get basalt. And there's lots of different kinds and whatever. But the point is, it's functioning the same. So we assume that this is going to be what the stuff inside Europa is made of. Now, it's also possible that you have a scenario where you actually don't have this, but you have the stuff that the basalt would have come from, mantle rock, essentially. But it turns out that from the perspective of how rocks behave, they're actually largely the same stuff. Chemically, they're not, but mechanically, they are. And the reason we cared about this is because the question was, what would the environment look like would it look like something you see on Earth? And where we see those hydrothermal black and white smokers, for example, on Earth, you see those in tectonically active parts of the ocean floor where there's a lot of fracturing and a lot of faulting. And the reason this is exciting is because when those fractures happen, they basically allow water to percolate down, seawater to percolate down, and it exposes that seawater to rock that has not already reacted with water, to what we call fresh rock. And in the process of producing this exposure of this water hitting this fresh rock, you can undergo chemical reactions that produce things like, for example, hydrogen. And there are microbes that live off this hydrogen, and they form the basis of this, essentially this food chain.
Now, is it like it's primarily those spots, but aren't there also hot spots that are just kind of at random locations around the world?
Yeah, there totally are. They totally are. And so a big part of this too is understanding what's their genesis. But what's very, very hard to escape from on Earth is that anywhere in the ocean floor, you are directly on Earth, you are indirectly or directly seeing the effects of plate tectonics. So for example, where we have these really, really hot hydrothermal black and white smoker systems, they are associated with spreading centers where basically new tectonic plates are being made, right? Where these plates are pulling themselves apart. And there's an enormous upwelling. In fact, 95% of the lava that comes out on Earth comes out in these settings. And together they're about 40,000 kilometer long chain all around the planet and the ocean floor. And so you have this enormous heat engine inside Earth with the mantle convecting and moving and driving this process of plate tectonics. And even far from these ridges, there are still huge fractures, really, really big ones. These are called transform faults that basically extend right out to the abyssal plains from which fluids will percolate. And if you actually look at bathymetric maps on the seafloor, you often see chains of volcanoes along these things because they're conduits for which this stuff can come up. Now, you also find lots of volcanoes that are totally randomly distributed. But you're also talking about a scenario where these are all happening on a very large planet, right? We are the largest rocky world that we recognize in the solar system. And so we shouldn't be surprised if 4.5 billion years after Earth's formation and birth, we still have a lot of geology happening. So the question then becomes, what are the conditions that would be required to have this kind of system on Europa? And what we find is that the conditions just aren't there. Even though there might be tidal heating and tidal processing happening, that's not enough for it to be actively driving tectonic deformation. In fact, for example, most of the tectonics in the ocean floor don't come from the tides from the moon. They come from this internal plate tectonics processes. So what we worked at for Europa was trying to figure out, are the conditions ripe for these kinds of really big, hot hydrothermal systems with lots of fracturing, that once the rock is exposed to the water and you undergo this chemical reaction that produces essentially what could be food for microbes, are you able to then expose continually new unreacted rock? Or does the system sort of just go to equilibrium and stop? And what we were able to show, again, using these models and our assumptions, is that even for scenarios where we are almost cartoonishly weakening the rock to try and make this happen, we are struggling to find a scenario, at least in the modern day, in which stuff is actually geologically happening at the ocean floor.
And in your paper, you identified a whole bunch of processes and you got really creative. Like you even brought in, say, serpentization. As a possible route that this could go. So can you talk about you threw sort of all these ideas at the problem to see if any of them would get you anything.
Right. So basically the thinking is the principle when we start with is tides, because that's what's doing stuff on Io, and it's what we know is deforming the icy shell for Europa and probably generating enough heating in the interior to stop the ocean from freezing, right? So you just have to get it above 0 Celsius. But that does not necessarily translate to actual tectonics, to faults and fractures. Essentially, and especially big enough ones that would allow the fresh, unreacted rock to be exposed. So we thought about tidal stresses.
And could just the ongoing radioactivity of the isotopes inside Europa also contribute to a liquid ocean?
Yeah, so there's definitely, if you measure the surface of Earth after a few meters down, right? So the upper few meters of Earth are influenced by the sun and solar diurnal heating. But once you go a few meters down, rock is so sufficiently thermally high enough inertia that it really isn't sensitive at all to the fact that there's an atmosphere and there's a sun. And most of the heat you're getting, about half of that heat comes from radioactive decay of minerals, principally in the mantle. And about half of it is from accretional energy from the birth of the planet, right? So you absolutely have that heat in there.
Right. And so you would theoretically end up with some kind of liquid ocean just because of that thermal
Not necessarily.
radiation.
Not
Okay.
necessarily. It depends. And it depends on your assumptions. It depends, for example, because we don't have a measure or a direct sample of what the ocean floor is made of in Europa. We don't know for sure that it has the same abundances of the radiogenic elements as, say, Earth does, right? If it was more, then it would be easier. If it had fewer or lower abundances, it would be harder. So it's not clear. But because, for example, it is possible that some of these bodies may not even have oceans. A paper came out in December proposing that, in fact, Titan might not have a global ocean.
Yeah, I want to get to Titan in a second because that's a 1-2 punch.
I mean,
to me,
these are difficult things to figure because you're all doing best guess, right? That's what this is. And so basically, the thinking goes, you could have enough heat in there to potentially keep the ocean from freezing, but that doesn't necessarily translate to there being kind of active geology happening, right? So we thought about tidal stresses, but there are other mechanisms too. For example, when these worlds, one of the things that characterizes, and arguably the thing that characterizes the geological history of the inner solar system bodies, is that they basically go from being very hot to being very cold, and everything that happens in between is all the geology. And we even know that Earth has likely been hotter in the interior in the past than it is today, because especially this radiogenic stuff will start to decay, and the rates of heating will drop very, very slowly, but they do. But we thought about what happens over time as these bodies cool. And one thing that I worked on earlier in my career was the Messenger mission to Mercury. And Mercury is the archetype of the body where its interior was originally hotter than it is today, even though it's still hot today. And Mercury has shrunk, just like as something cools on Earth, it will shrink. And in doing so, produces tectonic structures on the ocean floor. And so we thought about that process for Europa. We also thought about things like serpentinization. When rock and water interact, they generally will produce these chemical reactions, and they produce new minerals. And these minerals typically are a little bit volumetrically bigger than the minerals that were there before. And so things expand a little bit. And in the process of expansion, that actually produces a stress and produces fractures. And so we know that on Earth, where water and rock interacting, it's almost a way of sort of self-propagating these little fractures. And so we thought about that as a mechanism for which you could potentially keep fractures going and allow that water to percolate down. And we even thought about the idea that what if you have, so if you walk into an IKEA, at least I saw this last time I was there, and they have whatever the famous IKEA chair is. Well, I don't remember what it's called, right? But it's char. And the thing is, they have one in this box where it's under like a piston, and they show you how they test these things. And they just basically simulate someone getting in and out of this chair like 1,000,000 times. And the point is they're showing that like over 50 years, your chair will survive because we've tested it to destruction. I mean, this is done in the industry a lot. And we know that if you do stuff to any material, but including rocks, if you do stuff enough to them over not long enough time, you actually intrinsically damage them on an atomic scale, and you weaken them. And it's called fatigue loading, and it plays a role in all kinds of things. And we were like, well, what if the rock was somehow subject to tides that themselves didn't do very much, but they sort of intrinsically weakened the rock at a very, very fundamental level, and therefore makes the rock weaker? So we thought about that. And then we thought about, well, if the rock is wet, now this kind of gets to a catch-22 in a second. If you put water into a rock, you weaken the rock. And so we know that on Earth, on the ocean floor on Earth, that rock is wet all the way as far as we've bored. In fact, anywhere we've put mines, we find water. And any rock I have ever seen in 20 odd years of geology is fractured to hell. So we assume that the rocks on the ocean floor, without ever seen them, we assume that they're fractured, because if they weren't, they'd be much, much stronger. And we assume that they're wet, which chemically and physically makes them weaker. And we assume that wetness goes as far down as we can think, which we know on Earth is not the case. We know that the pores inside rock where that water could be will close under a certain pressure on Earth, both on land and in the water. We ignore that for our study. So we are assuming the rock is very weak. We assume that it has already chemically altered at least a bit because that makes it weaker. Now, of course, that also means that any energy that there was there has since been used, right? Has gone away. But let's presume that that's not a problem. So we are doing everything we can to stack the deck in favor of making that rock weak and fracturable such that water can percolate down. And even then, we can't make it work.
Right. Even if you add them all together?
It doesn't make a difference.
Wow.
Now, couple of important caveats. The title of the paper has the word today in it, because we want to be very clear to people. This is our best guess for what the current state of the moon is. There is evidence by observing how these things orbit with each other and how their orbits might change that over time, particularly Io and Europa, may have undergone what's called an orbital resonance that's different to the one they're in today, where for a time they could have egged each other on and actually encouraged quite a bit of heating inside both of them, more than there is today. So much so that actually things could have gotten extremely hot inside Europa at some point, maybe 2 billion years ago. Now, the good news is that might lead to a scenario where you actually had a lot of geology, maybe not quite as crazy as Io, because the effect of those tides will drop off rapidly over distance, right? And Io is closer to Jupiter than Europa is. So I don't think Europa is ever going to have the same feel that Io does for those tides. But you could imagine a scenario where at some point in the distant past, a lot more interesting stuff is happening inside Europa. The issue is these things may go in and out of these resonances. So you might have a scenario where for a time, that long, inexorable march towards heat death that I described that characterizes most things, that actually might not, strictly speaking, apply for some of these moons. That might be the overall trend, but there could be excursions where for a period of time, potentially a long time ago, there could have been a lot more stuff happening. And that could change. That would change our calculations. That would essentially allow a lot more stuff to happen. But then you get back to the kind of starting condition, which is that in the modern state, that isn't the case today. So that's probably not happening today. And moreover, if that did happen in the past, those rock-water interactions that are so important to sustain those chemosynthetic environments on Earth may have happened a very long time ago. And it may not be possible if there's any more unreacted rock left, even if there were bugs there today. Now, we also... I'm not qualified to say that there isn't some kind of weird alien microbe that could survive in some sort of dormant condition for a very long period of time. So we don't say, and we can't say in the paper that there's no life. We can probably say there's no space whales. Actually, I mean, that comes to an anecdote I want to share with you in a moment. But the idea is, what I think we can say with this paper is that things are severely challenged.
Right.
In the modern day. Inside Europa.
That there is dramatically less energy available to any kind of ecosystem down there under the ice.
Yes. It doesn't mean that there's none. Because, for example, we do know that there are hydrothermal systems that are relatively speaking cold. They're not nearly as hot as the so-called black and white smokers. They're still around 100 Celsius. But there are places on Earth, and in fact, most by volume hydrothermal systems in the ocean floor are these relatively colder ones. And it's where water is just seeping through and percolating through fractured rock. Now, you have to ask how did the fracturing happen in the first place? And in the case of Earth, plate tectonics is a very effective way of sending stresses through plate. But let's assume these rocks on Europa are fractured because it's, say, serpentinization. It's produced fractures. So you can imagine that there might be quite a lot of circulation, of hydrothermal circulation happening on Europa. The issue is, one, what the rates are. And they're probably not going to be as energetic as they would be if they were the really hot systems. And you've also got to wonder, too, that if these things have already formed and been there for a long time, is there any fresh unreacted rock left that water can access? There's probably a whole pile of fresh rock that water would love to get down to, but it might be too deep for that water to ever percolate down to. And so the question is, we're not saying there isn't hydrothermal circulation, but there's probably not going to be the types you see in the cartoons where you see the black and white smokers, and the stuff that is there is probably going to be lower energy. You also mentioned radioactivity. Radiolysis is a known way in which microbial life can survive by the decay and the production of radioactive byproducts. And as long as those materials are there, they don't need water at all. They can just sit there. But then, and we have not studied this yet in our work, what you're doing is you're taking what we would call the parameter space where you might find microbes, and we're closing off more and more of it. We're not saying there aren't corners where there could be things, but if there are those corners left, they're probably going to be subject to much lower rates of energy. And that's going to have a concomitant effect on what kinds of life this could be, and also how long it could survive. And that's a big part of this too. It's can you sustain an ecosystem?
Yeah. And so when you sort of cast your mind across other worlds in the solar system, you think about Mars. Obviously, there were big volcanoes on Mars once,
right,
but there doesn't appear to be any active volcanism on the planet today. And it
right,
could have been 5 billion years ago, it could have been 1 billion years ago. We
right,
kind of don't know when the volcanism ceased on Mars. And then your specialty, Venus, you have been poring over, and maybe there's a couple of sources of active volcanism on Venus, maybe, and that's a world that's the size of the Earth, and Earth has plate tectonics. So
yeah,
clearly you can have reduced volcanic surface activity on a world, even something as big as Venus.
Yeah. Although I will say, this is where something I think but cannot prove yet. My guess is that Venus is probably about as volcanically active as Earth.
Oh, okay.
It's not going to be manifest in quite the same way.
All
But
right, we'll prove it.
well, all I need is $1 billion for my balloon mission, and I can.
Okay.
But the idea is, like it probably shouldn't surprise us that the largest rocky world in the solar system, Earth, is the one that abounds with life, and that is known to be pretty volcanically active today. And exactly to your point, we know that there was widespread, large-scale volcanic activity on Mercury in the first billion years of solar system history before it functionally ended. Same for Mars. The youngest known flow on Mars is 2 million years old. So the chance of Mars erupting again, I'd say, is about 100%. There is absolutely going to be another volcanic eruption on Mars. But on human timescales, it's functionally dormant, right? And what that tells us is that if you were to make a plot on the y-axis of stuff coming out and the x-axis is time, you start off in the top left corner, and then very quickly for most of these worlds drop off. You're not at zero on the y-axis, but you're close to it, and then you're just skirting down asymptotically on the x-axis. Because what I think we're seeing is all the interesting stuff happens early on, and then it stops.
Yeah. So, with the discovery of the ocean on Enceladus, with this, I think there's been this narrative that you've got Pluto, you've got Ganymede, you've got Triton, that what about Sedna, that there are all of these worlds that have potentially tidal interactions, leftover heating from the radioactive elements, that ocean worlds could be more common than terrestrial planets. Are you here to potentially dunk on that dream too?
No.
Okay.
I think I am fine with the idea that, Pluto is a great example of a world that, by rights ought to just have a whole pile of craters and nothing else. And that's clearly not the case. I think it's one of the most exciting things in the last 20 years has been finding out just how weird Pluto looks. So we know that these worlds can survive longer than we might otherwise have thought they did. But the point I'd like to make is, this is an example of, say, this conversation comes up often when we present this at conferences. People will point out, well, the moon is known to be tectonically active. We know that the moon has quakes deep inside, and those quakes happen on human timescales because, thanks to the Apollo seismic experiments in the 1970s, we know that there were hundreds of quakes detected. Some of them were moderately deep, and some were really, really deep. Most of them are very, very small, but the moon is creaking. So surely that means that there surely is stuff happening at the ocean floor of Enceladus, and that it's got creaking in the inside. There's definitely creaking in the moon. But we do know from looking at the structures on the surface of the moon that even what we call geologically young structures in the moon are tens of millions of years old, if not 100 million years old, because on the moon, that's young.
So I guess I should have clarified my question then. It's not about necessarily the presence of liquid oceans. Right. It's the presence of life.
It's the presence of active geology.
Right.
So you can imagine a scenario where there could be dozens of these worlds where there are subsurface oceans, and those subsurface oceans are touching rock. And for a time, there must have been these chemical interactions. There's no way of avoiding that, I think. The question is, can you sustain those over long enough for life to arise and life to survive to today? And I think what the geological record is telling us is that's probably not the case. So the way I think of this is, again, the only world where we know is continuously active is Earth. And again, strongly suspect Venus. But again, pound for pound, they're almost the same size. So you can imagine that for these, there might be dozens of ocean worlds. That water is still water today, not ice, although, of course, that's an open question for some worlds. But that does not inherently mean that there's active seafloor volcanism and faulting and fresh rock being exposed that could sustain an ecosystem, a chemosynthetic ecosystem, for millions, much less billions of years.
Right. And so we talked about briefly that idea that Titan, the other research that had come out about Titan, that potentially Titan doesn't have a liquid ocean, it more has a slush.
Yes. Right. So basically we have long suspected that if you look at the cross section of Titan, there's the icy bit on the outside, which we can see with radar, and that we've taken photographs, Huygens, that we're going to send Dragonfly to. And then we think that there's a big rocky thing in the inside, deep inside. Whether that rock is in turn what we call differentiated into rock and metal is an open question. But certainly we think that touching that rock is what we call high pressure ice that would like to be water, but under the considerable overburden that pressing down from on top is actually now an ice that could even be a few tens of Celsius in temperature, but is still physically ice. And then perhaps between the outer ice and the lower ice, there's a liquid water layer, an ocean essentially. And this work that came out last month has proposed that on the basis of reanalyzing Cassini data, that in fact there's good evidence that there is no global ocean layer, that instead there's probably pockets of briny water interspersed in this ice shelf.
So does that have implications for what we've been thinking about as these ocean worlds? Like, so like a 1-2 punch, do you think?
Or is it just
Titan?
I don't think we know, and I think part of the reason is because one of the core things we need to be able to back out what the interiors of these things look like are high accuracy, high resolution spacecraft observations. And the way we get that is we send spacecraft normally to orbit or to fly by, preferably to orbit. Or in the case of, say, Clipper, it's kind of splitting the difference. It's not just doing a few flybys, it's doing a pile of dedicated flybys. Clipper will be able to give us a much better handle of what the interior structure is, using essentially very sophisticated geodesy, using how the radio signal to the spacecraft to Earth changes. And from that, you can do some very clever statistical analyses to work out what the interior structure has to be to explain how that radio signal changes. And in doing so, you get a much better handle of how it's differentiated and where stuff is. And it was a reanalysis of these data for Cassini and for Titan that suggested that, in fact, these data are consistent with there not being a global ocean. If we were able to send spacecraft to each of these worlds, to Sedna, to Pluto, to Ganymede, to Titania, Oberon, Triton. I mean, the dream is we would send dozens of these things out there. But if you have that ability, maybe you don't need to just fly by or orbit. Maybe you can land and carry a seismometer. But until and if we get to the point where we have these measurements, we're stuck with this best guess approach, where on the basis of available evidence, like here's the thing, if there's life inside Europa, great. Like, I don't care being wrong. That'd be fine.
Yes.
I'm not
going
to
like to be wrong.
But well, here's the thing. I don't know if I would.
Oh.
And this gets to the topic that I kind of wanted us to talk, which is the philosophy of this. Because when we talk about this, and by the way, we're working with a grad student who's close to submitting a paper where we're basically looking at a bunch of the other icy satellites, except other than Europa, using the same analysis. And we're finding essentially the same story. These are small worlds, and we perhaps shouldn't be surprised that not a lot happens on them 4.5 billion years into solar system history, even with tidal heating. But it gets to the question of when we were preparing press releases for this paper that came out, a lot of people asked, are you disappointed, or is this a bit of a letdown? And it kind of told me that and we see the same for Mars, and even when I read about how people felt when we discovered in the early 1960s that Venus was not this lush tropical world, but instead this absolute barren hellhole. The fact is that we are driven powerfully to want to find life beyond Earth. And I am. And honestly, on the balance of evidence, I can't imagine that it doesn't exist. But I don't know if it exists in the solar system, and I don't know if it exists today in the solar system. And that's part of the kind of the issue we're trying to get at with the timing of these processes. We're not saying there isn't life on Europa today. We're saying that it's challenging environmentally. We're definitely not saying there was never life on Europa. And like I said, if there were these earlier periods of heating and much more enhanced geology, there totally could have been. But I wonder if we're going to learn in the next 50 or 100 years that perhaps making life in the first instance isn't difficult. But what the real challenge is keeping it going over solar system history. One of the reasons of bringing samples back from Mars would be to try and help us understand the answer to that question.
Right. But I wonder, as your therapist now, why you're not only not disappointed, but almost, I don't know, you feel encouraged. Does it sort of cast a vision back to Venus that there's a place that has plenty of energy inputs and obviously has some downsides, but it has, but if you do really feel like it has max volcanism, has obviously mountains of solar irradiance, has a lot of active chemistry going on in its atmosphere, that's a place that shenanigans can happen.
Yeah, for sure. But at the same time, I don't know that it does, because there are real challenges environmentally to life in the clouds. Although there are also people who are doing some really exciting chemistry suggesting that there could be life a little bit as we don't know it, that might be there today. But at the same time, a lot of the work that I'm doing for Venus is thinking about what the ancient Venus could have looked like. And there is at least some evidence that is consistent with, does not prove, consistent with the idea that ancient Venus might actually have been more Earth-like than really anywhere else in the solar system, including ancient Mars. And so it kind of gets to the idea. So am I encouraged? I am, because I think this is helping us refine the question of where is there life? What conditions environmentally are required for life to emerge? And crucially, and this is the thing that I always try and help people understand when we think about the sheer deep time we're talking about. What does it take to keep life going once you have it? And, we talk about Mars as a place where we know billions of years ago, on the basis of these rover missions in particular, that there were lakes of water, standing bodies of water on Mars. We know there were hydrothermal systems. We know that impact craters are great places to look for that stuff because of the energy involved. I certainly absolutely cannot rule out that there was ever life on Mars. If there is life on Mars today, if there's native alien life on Mars, it's hard to imagine that it's not anywhere except deep underground. But because deeper underground, you could continue conceivably still on a world even as modestly small as Mars, still have enough hydrothermal and radioactive decay that there could be pockets of water and there could be life. So that's a possibility, right? And of course, if you look at Mars, even the rocky part of Europa is so much smaller. It's smaller than the moon. So again, maybe we shouldn't be that surprised by seeing these smaller worlds running out of energy sooner. But what I think is all of this is instructive in telling us where we should be looking at, both for today and in the past. So yeah, I'm not disencouraged by this at all, because A, if I'm wrong, great, there's alien bugs in the solar system, let's go see them. But B, if I'm right, doesn't mean there wasn't ever life there. It doesn't mean we're alone. It just means we have to be a bit more selective in where we're going to find it. But there is, like I said earlier, I worked on the Messenger mission for a long time, and Mercury will always hold a little place in my little dipshit planet that, most people haven't even seen, right? I love Mercury. But Mercury, no one seriously considering Mercury had or has life. But I think it's a fabulously interesting place to study. And it does bother me a little bit when so much of our discourse in planetary science generally is through the lens of life. Because although I think it is arguably the most profound question we can ask, it's not the only question we can ask. And for that reason, I would like us to not lose sight of the other really cool reasons to explore these places.
Yeah, I mean, I think it's sort of like an evolutionary process, pardon the pun, where a person comes at it in the beginning with these sort of really big picture questions, and all of the roads end up being unsatisfying. That essentially you get to the end of like, we don't know, and we kind of don't have the tools to come up with any kind of definitive answer. It is absolutely a scientific question, but we are not equipped to answer that question yet under the current funding, the current missions that we have available. So like absolutely, like put a bookmark there, and then let's get back to some of the other questions. And then I think you start to search around for the scientific questions that you can gain purchase on, geology questions, atmospheric questions, astrophysical questions, and those become very satisfying while you still have that, that big, deep philosophical question, are we alone in the universe? It sits on the shelf. You never forget about it, but you can make very satisfying progress in these other ways that bring you back together eventually to being able to chip away a little more at that deeper question. I'm working on a sort of idea for a video where a lot of the kinds of the modern advances that we're doing today in terms of searching for biosignatures and technosignatures and all this stuff, they had the seeds in the 50s, in the 60s. Mm-hmm. Even the ancient Greeks were thinking about these questions 2,500 years ago. And they had, like, for those of us in this modern age where we've got James Webb, we've got these telescopes right around the corner that can do what we need. Think about the poor Greeks who were waiting for 2,500 years for someone to say, are those other points of light, suns, and is there life on them? So So I would like to change gears briefly, and it's been about a year and a half since we've last talked, and when last we talked, you sort of had given us about a bunch of really interesting updates on Venus, on potential recent volcanic activity, and you just said, actually, I think it might be as active as Earth. So I would love to just spend a few minutes and just talk about sort of how the research on Venus is updated since we last talked, and potential missions and so on.
Sure, yeah, and this is an ever-changing landscape, pun very much intended. Yeah, for two reasons: one, probably a lot of volcanism happening, and two, the fate of these Venus missions, which we all celebrated coming up on 5 years ago, it is far from settled, and I'll come back to that in a second. So the Venus stuff that I'm doing is a lot of what I'm doing is focused on what you can tell from early Venus that's preserved in the highlands, which look to be very old. But a lot of work that folks in general are doing are thinking about, especially in light of a couple of papers that came out in the last 2 or 3 years, where people have gone back to the old Magellan data. So this is the mission that NASA operated Venus from 1990 to 1994. And it returned, to use the technical term, gobs of radar image data. Like there are parts of this planet that a human has not looked at since those data came back, because we do not have enough people studying this stuff. I mean, terabytes of this stuff.
Right. But crap resolution.
Surprisingly not. 100-meter resolution. Crap compared to what we're familiar with for parts of the moon and Mars today, where we have been spoiled by 25 centimeter per pixel. So that's true. But if you go back to where we had, say, for Mars or the moon in the 70s and 80s, where we were talking, say, 100-meter resolution, yeah, that's what we have for Venus. It's all we have for Venus right now. Boy, the stuff we're going to see when we get high resolution, it's going to blow our minds, right? But even then, with the 100-meter per pixel data, we can still see a lot. And something I tell my grad students when I find them crying at their desks is that, Venus is 3 times the land surface area of Earth. Like, there's a lot of land to look at, and there's some amazing stuff to do. And the paper that came out in 2023, a Herrick and Hensley paper came out, where they showed that over 2 successive imaging cycles that were about 8 months apart in the 1990s, that this huge, often we'll refer to it as a volcanic vent, but I like to tell people this is the size of the caldera at Kilauea, which, if you've ever been there, is freaking huge, and it doubled in size in 8 months. So this isn't a small volcanic pit. This is a gigantic freaking thing making an even bigger hole in the ground. And the fact that the spacecraft detected this unequivocally, because since the 90s, people have looked for evidence of volcanic change in successive imaging cycles. But the imaging and resolution is part of it. The quirks of radar data are another. But part of it was that Robbie Herrick, the lead author of this paper, had time during lockdown in the pandemic to just tool around in a GIS program these vast volumes of data. So I mean, this is where,
and was he like flicking the images back and forth to see if anything changed?
Yeah, essentially, you look at you try and compare. You take data that were acquired from different looked geometries. There's the weird, again, like I say, quirks of how radar are created. And you often, and people for years have reported seeing things appear to be different. But you have to be very careful to show that it's not just a function of the radar looking from a different direction, because that can show up different things. But once you can kind of rule that out, then you can start to kind of knuckle down and say, this actually looks to be a real change to the land. There's only a finite number of ways the land will change at the scale we could see it. And volcanism and tectonic activity are two of the leading processes. But that is to say that there's probably a whole pile of yet recognized areas where we also see change, where we just haven't had people having time to go and look for these things. But also Magellan wasn't really able to look for these things because, to your point, the resolution, it's pretty good, but it's not brilliant. And if we look at, say, the rates over months to year timeframes that, say, lava shapes the surface of Earth, it typically will do that, or often do that, at scales below what Magellan could see. So my reasoning for why I think Venus is about as volcanically active, plus or minus, as Earth is kind of geology 101. So again, this is like, it's professional expertise as opposed to quantitative science. It's almost as big as Earth. Why would it not be? And then if you look at the surface materials, and people have surveyed this, including folks I've worked with, we published a paper a few years ago where a former grad student of mine mapped 85,000 volcanoes on Venus. I mean, it was a lot. Again, something that she was able to do with the time she had in the pandemic. Again, machine learning and stuff can be brought to bear increasingly for these kinds of questions. But the point is that there are volcanoes everywhere you look on Venus. And many of these things appear to be sitting on top of everything else around them. And that suggests that they are geologically young. Now, the word geologically is doing a lot of lifting there, because I don't know, does that mean 10 years or a million years? But I can tell you this.
But they don't line up in the faults in the way that we see them on Earth.
In lots of places they do.
Oh, okay.
In lots of places they do. But the problem is that there are also places where there's so many faults and so many volcanoes that it's very difficult to be able to tell that any patterns you see, whether they're real or just happenstance, because you've got a whole pile of stuff there. So that is difficult to do. And it's the sort of thing that if we had another generation of Venus missions, which hopefully we will, and we'll come back to that in a second, that you potentially will be able to go and resolve these questions. But the way I frame it is that, even, like I said earlier, the youngest flow we think on Mars is about 2 million years old based on crater statistics. The likelihood of there not being another eruption ever is low for a planet that's 4,500 million years old. So the thinking goes that even if there were volcanoes on Venus that are 1 million years old, it seems unlikely that a planet almost the size of Earth would somehow have stopped only 1 million years ago. Now, the rate of that is another thing entirely, and there's work going back to the 90s suggesting that that the clouds in Venus are potentially volcanically replenished. So there's a lot of there's circumstantial evidence that on the balance of probability suggests that it's a very, very volcanically active world. That is not the same as being able to say that we know it is, but it's good enough, I think, to justify these missions and future ones thereafter to go and actually test these ideas.
Right. And like, let's imagine that you did get your $1 billion and you went shopping for scientific instruments and you were able to deploy them on your balloon as you are hoping. What kind of technology would get you what kind of resolution on the surface of Venus?
Right. So so if I only had the billion, he says.
If I have 5 billion, whatever.
Oh, great.
It's fine.
Well, then I'm going to do a bunch of orbiters as well, and I'm probably going to do some aircraft. But the nice thing about it is, if you want to try and answer the volcano question in particular, it turns out that happily there's a whole pile of parallel ways you could do this. So, for example, you could measure chemical changes in the atmosphere, which you could do from an orbiter, or ideally better from a balloon, or some kind of aerial vehicle. The balloon would be the relatively, I don't want to say most straightforward, least awfully hard thing to do. But ultimately, you can imagine in the future we would have fixed wing aircraft and whatnot. But you would look for changes in the atmosphere's chemistry, because on Earth we know the volcanoes often pump out SO2 and CO2 and a whole pile of H2O, a whole pile of stuff, so you could measure this. You would also look for, if you had the ability to image either high resolution from orbit or getting under the cloud deck and imaging stuff would be really exciting. You would look for, are there places where, and there's different ways you could do it. You could take images, regular images, that would tell you whether the land has changed over time. But you could also use essentially thermal infrared cameras, and you would look for areas, although the surface is very, very hot, it's still quite a bit cooler than a lava flow. So a lava flow will still pop if it's there. So you could do that kind of imaging. And then one thing that really excites me, and this is something that people have demonstrated on Earth through that repeatedly, is that if you put very sensitive air pressure sensors on a balloon, they essentially function as seismometers. They are basically barometers. They are measuring changes in pressure. And you can use what's called infrasound. And you would listen for volcanic eruptions. And people have done this on Earth now several times to validate the technology. So the idea is that you would put on your balloon or your fixed wing vehicle or whatever it is, mass spectrometers, so that would be able to tell you what the atmosphere chemistry is and how that chemistry would change, if it's changing. You would be able to potentially put imagers that would peer under the clouds, or you could deploy them. And you would also put these infrasound sensors on that would listen. And you wouldn't just hear volcanoes. You would hear potentially things exploding in the atmosphere. You might hear earthquakes. You might hear landslides, or even the noise of the wind moving over the mountains.
Lightning.
If it's there, you detect it. And then, of course, the really cool thing is if you look for lightning, you'd also put a magnetometer on your balloon, and then you would listen out for these electromagnetic pulses that would happen that would be potentially accompanied by a loud boom if you happen to hear a thunder peal.
But I think about those images from the 1990s from Magellan. And as we said, the resolution at 100 meters per pixel, but they're really nice pictures of the surface of Venus. So is there a go to the store, buy the newest edition of that, what is it? It's a radar array. Could you go and what would the most modern version in a new version of Magellan that, is now in orbit around Venus, does that get you to 10 meters, 1 meter? How good could you get?
A lot of it depends on how big the radar array is and also the frequencies at which it's operating. So Magellan, you could have designed a 10-meter resolution radar back then. The issue, there's a few issues to it, and the ultimate issue is money. Because if you have a larger spacecraft, you could have a larger array, or you could have a more powerful array that would have more energy in that pulse that you send down and come back. You could do much more today, sophisticated onboard processing. So you have solid state drives. You could use Snapdragon processors on your spacecraft, right? These things are becoming to be space rated now. And of course, the other issue is that the more data you take and the finer the spatial resolution, the bigger the file. And so you need to have make sure that the radio is better. And what the Psyche mission is carrying, for example, this deep space optical communications concept, is using lasers to basically make that collimated beam very, very fine. And we now know that Psyche, as a test, not the mission, but this instrument on Psyche, has demonstrated successfully that laser communication from deep space is an extremely effective way of communicating large volumes of data, or small volumes of data from really far away. But if you're at Venus, you're not that far away. But if you are going to send back terabytes of data, having a big ass radio antenna and lots of time in the deep space network is important. So the modern ways of doing this, it's not just that the spatial resolution gets better, it's our tracking of the spacecraft is improved, so we can make the images line up better. And it also means that the signal to noise ratio is better, so the quality of the image improves too. So yeah, modern radar technology, a mission going to Venus today, and hopefully we will have these missions fly, are benefiting from 40 years of technology improvement to develop these images. And when we get them, they're going to be of a clarity and a spatial scale that will blow our minds, because every time we've ever seen the moon or Mars or Earth or anywhere else at higher resolution than before, we've seen things that we didn't even we have 40 years of science questions for Venus that we know we can answer.
Right.
There's
we
a
just
whole
get higher resolution.
Yeah. And that's going to raise 40 more years of questions we didn't even think to ask yet, because we don't know what to ask.
Yeah.
I mean, it's going to blow our minds when we get these. The issue is whether these missions fly.
So does anyone give you a hard time about your pronunciation of the word lava?
Yeah, all the time. Yeah, and I see it's basalt, it's lava, it's not lava.
Yeah.
And also a big thing I'm focusing on right now for Venus is these things. Well, so on Earth we have these things called cratons, which is sort of the interiors of continents.
Yeah.
But in North America they're called cratons.
Yeah. So as a Canadian, as West Coast Canadian, I say lava. I say pasta. I say Mazda.
Yeah, yeah.
And
the palm of your hand. Yeah.
And that the root is clearly whatever it, where our overlapping accents come from. Yeah. But it drives Americans bananas every time I say the word, because I sound like an American most of the time, I guess. And then I say I have these various sort of idiosyncrasies,
quirky little pronunciations.
Yeah, exactly. Little pronunciations. I'll say Chesterfield. I'll say lieutenant, and I will say lava. And they're like, "No, dummy, it's lava."
Lava. Yeah. Well, that's if you want to call it, that's fine.
Feel free.
Yeah, I teach my students, I'm like, this is the X, Y, and Z axis.
Yes.
You're welcome to call it the Z axis if you wish. By the way, also, one of the short-lived but very, very high energy heat-producing radioactive elements early in solar system history is 26 aluminium.
Yep.
They may hear of it as aluminum.
Yeah.
That's fine. Yeah. But it's 26 aluminium.
Yeah. Yeah. The redshift, the Z, Z, redshift number Z.
High Z numbers.
Yeah, exactly.
Yeah. Unapologetic is my answer to that question.
Yes, me too. Right? Like, come on, and I plan to take a video where I'll just walk around to random people in my city and say this word. And then they'll all say it. Most of them will say it very similar to me. And then it'll be case closed. I have an accent.
Yes, exactly.
Right?
Exactly. Yes.
So it's not that I'm saying it wrong. It's that I just have an accent.
Exactly. But I think life would be very boring if we were completely homogenized. So
yes, totally.
That's the justification I use to say I'm going to take the lift, not the elevator.
Paul, the question I always ask you, what are you obsessed with right now?
Right now, I'm actually thinking a lot about exoplanets. A lot about exoplanets. And one of the reasons why is because we are at the point where we're getting more and more data from JWST. People are really standing up now thinking about habitable worlds. And we're thinking, we the community, about what these worlds might be like. And I think we are on the cusp of, we're starting to see a thing happening that last happened in the 1960s, which is when worlds that up to that point were exclusively the domain of people with telescopes, that were points of light in the solar system, began to emerge as real worlds with their own distinct features and personalities, because we started sending spacecraft there. Now, we are a very, very long time from sending spacecraft to exoplanets, but we are beginning to learn more of them as not just population level measurements, but starting to understand and tease out different properties of different worlds. And that really excites me, because what I think we're going to start seeing is, I think we're going to see the same themes, but we're going to see variations in those themes in these other planetary systems. And even the issue of, could you have life on a large world, perhaps not Europa size, but a much larger version? What if Earth had 10 kilometers of ocean on top of it and no land at all? I think it'd be very unlikely that you wouldn't have life on a world like that. And so it's thinking about, if I change this parameter or that parameter, if I make a bigger Mars or a colder Venus, what's the outcome? And that stuff really drives me. And so the more and more we're learning about these other exosolar planets, the more excited I get. And the more valuable this system becomes to help us understand just what those variations are.
Yeah, that's been my kind of obsession, is this idea that Venus is the best example of an exoplanet that we have, that we can study this world and all of the kinds of assumptions and the difficulties that we're having just analyzing this world that is right over there has implications for us attempting to come up with any kind of certain understanding about these exoplanets.
100%.
That if you're still going to argue about the presence of phosphine in the atmosphere of Venus, be ready for ambiguity in your detection of anything, sulfur dioxide, whatever, right?
And socializing that message is a really powerful thing to do, because it helps people understand just how little we understand about these worlds. We have, I think, we've got the 0th order understanding of Venus down, modern Venus. But even in the context, this comes back to the whole issue with Europa or generally extraterrestrial life. Let's say it comes to pass that we find out eventually that one of these two scenarios for Venus is that it started off terrible. Let's say we find that that's the answer. In which case, maybe, and we've discussed this before, its distance to the sun is, let's say, the principal reason why. That means that we might have a reasonable assumption for what we'd find in other systems, and it might guide our seeking of, if not necessarily life, but perhaps habitability, let's say, or environments that are potentially amenable to life. If we find that Venus was originally more Earth-like, maybe never truly like Earth, but not like it is today, and then it changed, it's another example of a world that has undergone profound changes, like Mars, and potentially Europa. If it had been more, never Earth-like, but more clement, more habitable in the past, and it's not today. And it might yet be in the future if another one of these orbital resonances happen. So you can imagine this idea, and this is what I think we're beginning to see, that maybe the issue isn't so much that it's not hard to make life. Maybe the issue is that it's really, really hard to sustain it. And that sustaining a habitable environment over billions of years is extremely challenging. And that's where exoplanets are really, really going to be valuable, because, to your point, Venus then becomes the linchpin in this. Understanding if Venus changed and why and when has enormous implications, not just for Venus or for other planets, but even our own world. And if it turns out that it's always been terrible, well, then that also holds evidence that our world probably is unique, or at least very rare, and that in turn will guide our search for life elsewhere.
Yeah, and I guess that there are, when you think about, there are potentially hundreds of millions of terrestrial planets within the habitable zone of their star. We have 3 of them here in the solar system.
Right. They're all different.
But they're all different, yes. And yet there are a few things, like, for example, the Earth has a large moon.
Yeah.
That it has an intrinsic magnetic field, that it has a certain consistency of amount of water compared to rock and metal and so on. And it could be that it's some of those weird little edge cases that end up being a lot more important than we ever thought for the habitability of our planet.
And it could be that size may not matter as much, or its stellar distance might not matter too much. Exactly. But we cannot fill that question in with only the solar system. We simply don't have enough ends. We need more. And so that's the real power of that comparative planetology in exoplanetary science.
Yeah. I mean, right now, you think about the geologists, they now have 6,000 worlds to work with.
That is what, you asked me what I'm obsessed about. That's what I'm obsessed about.
Yeah. Awesome. Well, Paul, always a pleasure. Good luck with your work on Venus. I can't wait to I'll let you know when the funding comes through on your fleet of spacecraft
and I'll be down
for Venus.
To Best Buy, pick up some radios.
That sounds good.
We're always working towards things. And right now, there's a big push in the community to try and get support behind these missions. NASA's facing potentially much less of a cut than we were worried about even 9 months ago.
Yep.
But the fate of these missions is not certain. And, it's a whole other conversation about where things are vis-a-vis NASA's planetary portfolio and what that would mean going forward. But, if I am nothing if not stubborn, and I will continue to do my bit to get a fleet to Venus.
Yes.
Because there's a bunch of unanswered questions and we should spend time there. That doesn't mean it's not the only place we should look. We should be sending spacecraft to other places as well. But certainly I would like to see Venus be a place we really start to go back to.
Well, I'm on board. You convinced me. I'm on.
Awesome. I appreciate
the plan. All right. Thanks, man.
Thanks, Razor.
I hope you enjoyed this conversation with Dr. Paul Byrne. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bailock, Cy Nelson, Dark Finga, David Gilton and David Matz, Evan Pro, Greg Feely, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Smith, Michael Purcell, Nordspace, OneStepForAnimals.org, Paul Robach, Ren Kaidu, Richard Williams, Sean Sargent, Stephen Fryland Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldabor Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So I just want to say what a treasure Paul Byrne is. We have chatted many times. I've interviewed him in the past. He was a regular participant in the weekly space hangout that we were doing a couple of years ago. And generally, when I see one of his new papers, I know that it's going to be interesting, and his explanation of it is going to be great. And I think, his superpower, and if you go and follow him on Blue Sky, you will see the kinds of posts that he does. He is continuously looking for ways to connect the kinds of academic research that he and his team are doing with the sort of the endless hunger of the public to be able to understand more about the cosmos around us. And he is this conduit, taking what are fairly intricate ideas and then making them very accessible to a wider audience. And, if there are other people, if you're a scientist and you are, you have this interest in that public communication side as well, you want to try and share your enthusiasm for the field that you're working on because you know that it has an impact, it has ramifications, that it can feed this curiosity that's out there. Take a look at what Paul does and sort of use him as an inspiration for being both an effective scientist and an effective communicator of that science. If there's anyone out there who kind of exhibits that spirit of Carl Sagan, Paul Byrne is one of those people, and definitely check out his work. All right, we'll see you next time.